Today we're measuring the flicker measurement capability of the bolt. It's the flicker standard that we're using is IEEE 1453, and in our test setup we have a bolt that is connected to an AC power supply, and we can program this power supply with arbitrary levels of voltage variation that should generate known flicker metrics. And to verify our setup, we have two incandescent bulbs powered from the AC source and an optical sensor feeding into the oscilloscope as a separate measurement of the amount of optical light change output from the filaments when we subject it to different RMS voltage variations. You can see the flicker now. We are actually around a flicker level of 2, which is twice the threshold of irritability per IEEE 1453. And we are going to go through the conformance test that is specified in 1453 and also do some extra testing on the bolt to make sure that the implementation is good. So here's a spot check. This should be around 2.2, and it is reading 2.2. We're using PQ Canvas to get live readings from the bolt. The flicker readings are slow because the standard calls for a 10-minute reading. So it takes a minimum of 10 minutes to get a new value once the level has changed per the standard. Now, we're going to go through the conformance test that is in the standard. And IEEE 1453 gives a list of 29 voltage changes patterns, and each of these should read a PST of 1 plus or minus 0.05. And these range in value from less than 1 change per minute, as many as or as long as 1 every 10 minutes, all the way to several thousand changes per minute. So we're in the 10 to 20 hertz range here. Though it takes quite a bit of time to go through every level in the table because each one takes a minimum of 20 minutes to generate a valid reading. So we've done that. We've subjected the bolt to all 29 of these readings, and we've let this accumulate in PQ Canvas. So we have a PQ Canvas recording. And here we're looking at min, max, and average voltage for all 3 channels throughout the conformance test. And you can see that it's over a 24-hour period to generate this data. Now, each of these patterns should generate a PST of 1 plus or minus 0.05 per the standard. So let's see how the bolt has computed the flicker. This is the flicker overview graph, which is a summary of the voltage changes. So here on the top we have all 3 channels tied together, and we're looking at min, max, and average. And the middle trace is PST. The bottom trace is PLT, the long-term flicker. So if we zoom in on the test portion, we can see that as the voltage is varying from very large but very slow changes to smaller and smaller changes and then widening up a little bit, PST is well within 1 plus or minus 0.05, and so is PLT. So the bolt has passed the flicker conformance test per IEEE 1453, but we want to go a bit beyond that. We want to go beyond the minimum. We're going to check the dynamic range of the bolt flicker measurement and also check its linearity to make sure that it is valid not just at PST of 1, but also at very low flicker levels and very high flicker levels. So we're going to set the power source to a very small change. This should be a PST of 0.2, which is the lower value that a flicker meter is meant to measure. And we set this, you can see the flicker is almost invisible. Even on the optical sensor, it's difficult to see because this is a very small amount of flicker, the smallest that's measurable for the standard. And we will wait the appropriate amount of time for the calculations to happen. Again, the value is only updated per standard every 10 minutes. So we will come back here in a few minutes and check the bolt's measurement to make sure it's measuring 0.2. So we've waited for the flicker calculations to complete, and we are reading a PST of 0.20. So we've shown the low end of the bolt flicker measurement ability is good. And now we're going to check the other end of the scale to make sure we have a wide dynamic range. We're going to go to a PST of 20, which is an extreme level of flicker, to make sure the bolt has enough dynamic range to cover the very low levels that you might see and very, very high levels. So let's set the source for that. Now we are have a very visible amount of flicker. You can very easily see it in lights. You can very easily see it on the scope. And we will let the bolt process this data and make sure that it's going to be measuring well on the high end. Right now we are checking the bolt's very high flicker level measurement. We have a 20% voltage change. We can see a very large change in light output from the sensor because this is a huge amount of flicker. We check here in PQ Canvas, We're measuring 21, which is the right amount for this level of flicker. That's the top end of the recommendation for the dynamic range of a flicker meter. All right, now we're testing an intermediate level of flicker. This is a PST of 4, well beyond the threshold of irritability, and you can see the lights flickering. The optical sensor is showing clear changes in light output. Let's make sure the volt is measuring this correctly, and we can see that the volt is reading 3.97, 3.98 on all 3 channels. The volt is successfully measured flicker at this high but intermediate level. All right, we've fully tested the bolt's flicker measurement ability, and it's passed the flying colors. It met all the conformance test requirements that are in IEEE 1453, and we've gone beyond that to test its linearity and ability to measure very low amounts of flicker and very high amounts of flicker. So it has a good dynamic range also. So the bolt is perfectly suited for quantifying a flicker per IEEE and IEC standards.